Okay. So we have, the last lecture normally would be, I think, April 23rd. That sound about right? Because after that, classes sort of ended on the, soon after that. So that I will actually not be around for the last lecture. So our last lecture will actually be April 21st. Okay, which is a Tuesday, which means we have basically 5 lectures left. So among the things I want to cover are so as I mentioned, we finished our whole discussion of how to do clustering at scale, and of course one could say more, but I think what I try to do is give you the basic tools that get used when you're doing clustering at scale. And I think we've covered more or less the tools. If you now start looking at how do you do clustering in a MapReduce setting or using Spark, they basically use the same ideas, idea of clustering clusters and sampling tricks and things like that, right? So we're not going to see too much in the way of difference in methods. So what I want to do now for the next few lectures that we have left is talk about some specific topics that we haven't really covered properly in the class that I feel like it's worth covering, just to give you a sense of what else is out there. One important topic that keeps coming up, which we'll talk about today, is clustering with outliers. And I'll say more about why this is an important question. It should be hopefully reasonably clear that this is an important question for you. Another question that I'm going to be looking at, and again, I alluded to it many times, but I haven't really spent any time talking about issues regarding this in general, is to do with soft clustering. So in other words, clustering where you don't require a hard assignment of a point to a cluster. Right, so again, we've seen this happen when you do the learning mixtures of Gaussians and so on. You get the results you get are these kind of assignments of points to different clusters. But I think it's interesting to look at it as a first order object and understand why it is that. What's interesting about this, how is it different from just a hard clustering, what problems come up when you deal with soft clusterings, and so on. I also want to spend a little bit of time talking about graph clustering. Now we've of course have already seen spectral clustering, which is one way of thinking about graph clustering. It's really about similarity data, but you then think of it as a graph into a Gaussian. But there are many other questions that come up when clustering graphs, and I think some of these questions are interesting to explore because they treat a graph in many ways as kind of a social network, and so I think it's good to understand what clusters actually mean in those settings. You're not just thinking of it as a similarity structure in space. And I think that's basically it. I mean, I'm hoping that together with these 3 things we'll span 4 of the 5 lectures, then we'll have a last lecture sort of review to see what we've learned. And that should basically cover it as far as what's left in the course. Okay. All right, so on that note, let's talk today about clustering with outliers. Okay. So we've seen all along, right, that when we have data, we have various assumptions about how cluster related it is. We've talked about different ways of dealing with this, different kinds of cost functions, different ways of handling noise in the data. For example, right in the beginning, we talked about doing k-center clustering, where you want to minimize the max time radius of a cluster. And then we said, well, if you have a few points that are noisy, that could really mess up your notion of a max radius, because you'll just pull the points out. And we said, okay, we'll use something like k-median, which is a sum, because intuitively it's somehow is supposed to be more robust to outliers. So we've seen various ways of dealing with outliers in data. And the k-median approach in some sense is a way of saying, well, we don't know what the outliers are, but we'll make a cost function somehow capture them nicely. Which is a kind of indirect way of thinking about this. And I mentioned a long time ago back then, I said, we'll talk about other ways of doing it. So now is the time. So again, just to repeat, I mean, we know that outliers are a problem in your clustering because if you have a bunch of clusters and they have a nice cost, something here. If I now put one extra point in somewhere, then if you, for example, you're doing k-center clustering, you're going to have to adapt your cluster now to take into account this point. Because if I only give you 2 clusters, for example, my budget is only 2, I have to make a decision. Either I put these 2 groups in one cluster and this by itself, which doesn't seem like a good idea, or I have to pull this into one of these clusters. And now my cost becomes this much larger cost. And it's just, much more than the cost we have there, right? Maybe that should have been it. And so this increase in cost, right, has, in some sense, has two effects, right? First of all, it messes up your costs, right? But it has a worse problem in that it basically is telling your algorithm, we're not going to be able to do better than this value of R because we have this problem here. So, I mean, the algorithm's not actually thinking this, but if you think of the optimization landscape of any clustering function, it's saying somehow there is a global minimum of R, which is very big, which essentially means that it has kind of license to do whatever it wants. So, if you have let's say this is my landscape of clustering cost, right? So think of this as idealized over all possible clusterings, and I have some kind of landscape of clustering cost. And this is my global optimum. And I'd like to get close to this. If you introduce outliers into this problem, right? And now what you're saying is that, in fact, this cost is going to go up to be something like, I don't know, something like this. Something like this. Then not only have you removed the point you would have been able to find, you're also now allowing the algorithm to find other solutions which might look good now, but could be very terrible. So in other words, it's not merely that the cost of your solution might go up. You could still live with that if you actually found the solution and you could inspect the answer and say, okay, look, this point is clearly an outlier. What's worse is that because the cost has gone up, your clustering result itself could be very messy. Because now the algorithm doesn't need to find a good solution in some sense. So there's two reasons why in some outliers are a bad thing, not just in terms of cost, but in terms of the actual thing you produce at the end of it. Your meaning of your clustering actually changes. And it's not hard to see that even with something like k-means, this could happen, right? With k-means clustering, yes, you're taking the average of distances to the cluster center, but as you move points out, things can be pulled out. With k-meaning, this happens less, but it can still happen eventually if you have enough points going out. And so we want ways of dealing with outliers explicitly. We don't want some implicit way based on designing a clever cost function. We want an explicit way of dealing with outliers that we can just get rid of from the problem altogether before we start doing any processing. And again, there are many reasons why this would be a good thing. First of all, it cleans up your data. Secondly, maybe your outliers are not a large set, but they're large enough that they tax the resources of your algorithm. So it'd be good to get rid of them so that your data size reduces, so things will get a bit more efficient. And it won't pollute things later down the pipeline. So the question is, how do we do this? How might we go about removing outliers? And of course, before we do that, we should be able to define what an outlier actually is. And that's another problem. What is an outlier? Right? So, I mean, it's easy to say, oh, well, a point that's very far away from everything else is an outlier. But that's not necessarily a satisfactory answer, because you could have a data set where everything is kind of far from each other. This could be viewed as a very good clustering. It's not, these points are not outliers. And another way of thinking about this is that if I have a bunch of points here, okay, and let's say this is a Gaussian cluster, right? Now, so I have some point here. You probably wouldn't call this an outlier at all. It's just something on the border of, within 1 standard deviation or 2 standard deviations away from the center. But suppose this point starts moving out. I think at some point you'll agree, okay, this looks like an outlier. If you just look at it, it'll seem like an outlier. But what about here? Is an outlier here? Is an outlier there still with respect to that cluster?
It depends how you define.
I'm just asking you to look at it. No, I mean, I don't have a definition. I'm just going to look at it. Eyeball it. What do you think?
May or may not.
Yes, it is.
It is. Okay, good. So, see, don't waffle. It is. Suppose it's here.
No, I cannot.
Okay, fine. I mean, there's a good point, right? What I'm trying to say is that as you get closer and closer, at some point it stops being an outlier. And there's no good reason to say, well, now it's an outlier, then it wasn't, right? So, even if we would like to remove outliers from a data set before we cluster, it is not clear how to define an outlier independent of the clustering itself. We think there should be some way, but it's not clear how to do it. So we first have to define the notion of outlier before we can start talking about how to find it. So what do you think? Defining outliers. What do you think we should do? How would we define an outlier for a data set? And again, you will find, as we will see in this lecture, that we're not going to try to be very clever right now in the process of defining it. We're going to, a natural definition of an outlier is going to evolve from the algorithms we use. But we're not going to really specify it very clearly up front. Having said that, so don't try to get too cute when defining the outlier. What if we have very basic sort of, something really almost dumb definition of an outlier? Or rather, a definition of clustering with outliers. Let me say that slightly different. Why not asking for a definition of outlier? What does it mean to do clustering with outliers? Any thoughts?
The very basic definition could be the point which is outlier will be far from all the points.
Right.
So basically you calculate the distance between.
So
all
this is
the
the problem,
points
right?
and
Think
then-
of how Gonzalez's algorithm for K-center works. It takes a point, finds its farthest neighbor, and we're calling those points the cluster centers. Not only are they not outliers, they're the chiefs of their clusters. So your definition captures, not just what you would like to consider outliers, but things that are the core of the clustering algorithm itself. And again, you're all focusing on the semantics of an outlier, right? That's somehow far away. Suppose I told you not to think about that. Is there another aspect of an outlier that we would agree on is something that outliers have? That has nothing to do with how far away it is from anything?
Density. There should be
Explain.
less
Go.
points in that around area.
There are less points around the area, so it should be kind of far away from things?
One thing is that we are far, and then also that area should have like very.
But isn't that the same thing? If it's far away from everything, then it won't have anything nearby, right?
No, I mean very less points far away.
Very less points.
That cannot be assigned as a cluster center also by that algorithm.
They cannot be assigned as a cluster center. But if they're far away, they could be, right? So what will stop them from being assigned as a cluster center if they're far away from all the other points? I think that's an idea that I'm trying to pull out from what you're saying. So, you said it's something that's far away, but then I would pick it, right? As far as like a Gonzalez algorithm, I would pick that one, wouldn't I? Why would I not pick it?
Okay. So again, we define outliers as something so dissimilar from everything else that it is almost like an alien in a group of humans.
Yes, but that's the point that they're making. I'm trying to say, don't think,
That's
because
right.
we don't yet have a way of talking about that in a reasonable way.
Very philosophical.
Huh?
Very philosophical point.
It's they're ET, Yeah. But that's fine. But I'm saying that's one definite aspect. What Samira is mentioning is getting to a different aspect of what makes something an outlier, to do with densities and counts. So let me just say it, right? I mean, you don't expect to have too many outliers. If you have too many points that are calling outliers, there's something wrong with your definition. If 1/3 of your points are outliers by your definition of being alien, then maybe you should redefine alien. Not redefine, So in other words, outliers are both things that are dissimilar, but they're rare. And I want to focus on the second part rather than the first part. Mainly because I don't quite know how to define the first part just yet. So outliers are unusual and rare. Okay? You expect to have very few of them. You don't expect to have a lot of outliers. Because that goes to the clusterability of your data itself. If I told you there were very few outliers in a data set, might that give you the idea for an algorithm? Again, something very, very simple. Not very smart, just, But if I tell you yes.
If you find a cluster with one element, then it's an outlier.
But what's the algorithm for clustering with outliers? But if I tell you that there are very few outliers in a data set.
Cluster it, and then if you have any clusters with one center, throw them away and then recluster.
Okay, that's one way of doing it. So that's a way of doing clustering where you say, I will ignore the fact up front that I have outliers. So this is strategy one, right? So ignore outliers, cluster the data, and then inspect. Right? And it might work, but it also could distract you for the reasons I mentioned. That if you have a few outliers that are really bad, they could just change your clustering structure altogether. If you flip this around, there's another algorithm you could use. So you flip this around. So this algorithm basically says cluster first and then look at outliers. The opposite would be to look at outliers first and then cluster. If I told you there were very few outliers, here's what you could do. Guess the set of outliers. And then cluster. After removing them, of course. So what does that mean to guess a set of outliers? Of course, when we say guess when we do algorithms, we don't mean to guess. We mean try all possibilities. Suppose suppose I tell you this data set has one outlier in it. What could you try to do? You could say, oh well, maybe this point is the outlier. So we throw it out in cluster. You say, oh, maybe this point is the outlier. Throw it in cluster. I didn't say this was a smart algorithm. But it will work in the sense that you eventually will pick the right point. And presumably if it's an outlier, the clustering cost of what you get will be quite small. So in particular, if you did this all for each possible guess and took the best value you get on the result, you would find the outlier. And so if your set of outliers is really small, you could imagine doing this. Right? Of course, the running time, suppose you have z outliers, is going to be something like n choose z times the time for running a clustering. Let's say n minus z points. That's not going to be great at all. If your z is more than 2 or 3, that's not going to work. So there are two strategies that we have, basically, that you think of as extreme points in this process. One is when you first fix all the outliers ahead of time, remove them by some process. First guess them by some process and then remove them, and then do your clustering. Or you cluster first and then look at the results of clustering and try to inspect it to say, okay, this cluster looks like there are a few straggly points. If I remove them, in fact, you could run essentially this on each cluster. You could say, okay, for each cluster, there are a couple of points that are causing lots of trouble. But now I can deal with more points because I have, presumably more clusters. Even if I have 2 points in each cluster, I can deal with 2k outliers instead of just 2. And it's a bit easier.
So the outlier points are those points that removing them make the cost very different or no less different?
They make, so good. So what this is implying is that removing the outliers makes the cost very different, but we don't expect them to change the structure so much. But if we put them in with the wrong cost function, they could change the structure a little bit, just because the cost function gets distracted by the outliers. Does that make sense? Nominally you're thinking that outliers are things that don't really affect the structure of the clustering, but affect the cost of the clustering. But by virtue of affecting the cost, they could affect that your algorithm being imperfect could then get distracted. So that's why you might want to try and find these things early on. But again, you have this problem that it takes too long to do it. So in an ideal world, this is what we prefer, right? Get rid of them first. But that doesn't seem like it's an easy thing to do. Right? And this is the compromise solution, but this also has its own problems. Okay. And there are another way to generalize this idea, right? A third way, sort of to deal with outliers, is to say, let's maybe you have some information about your data, right? All data points not treated the same. You have some information, and maybe you have some weight function. So now you're saying that you want to cluster, let's say these are set at points minus some set z, which is your outlier set, such that the sum of all weights, so let's say pi belongs to z, wi is less than or equal to some threshold. Right? So in other words, you could generalize either of these notions, or at least the second notion you could generalize to say, it's not a particular number of points I'm looking for to exclude, but it's a total weight of points I'm looking for to exclude. So points are different weights, and I want to exclude points of total weight that's small, because they're somewhat insignificant. This is useful if you have some points you know are very important, so they have high weights, you would never throw them out. And then there are other points of small weight that you have some choices between, so it might allow you to narrow things down a bit. And of course, if all the weights are 1, then this goes back to this case. So you can think of generalizing this Z, which is a count, a cardinality, to a total weight. Right? And this turns out to be useful in certain methods, and we'll briefly allude to this later.
So when the weight is given to you.
Yeah, the
then
weight will
it's
be
useful.
given to you, for example. Right? So maybe you have some prior belief of what the importance of your points, or at least some of the points you believe are very important, so they have a non-trivial weight, and the rest you say, okay, I weight 1.
Okay.
So you can get a bit more nuance in this definition. Of course, this combinatorial argument doesn't go through anymore, because now you're talking about the partition function rather than just an n choose z kind of thing. But at least you might be able to emphasize that some points will never be thrown away. So this the set you're choosing from goes down by that. All right. So what should we do? The weird thing about clustering with outliers is this sort of paradox that on the one hand, you're telling your algorithm you're allowed to ignore some points. So maybe that makes your job a little bit easier, because points that are giving you a hard time in clustering you can ignore. But on the other hand, the optimal solution that wants to find this best answer is also able to do the same thing. So in some sense, you've increased your problems. Not only do you have to find a good clustering, and we've seen how hard that can be, you also have to decide which points to remove from it. So you've created 2 problems when you originally had 1 problem. And so that's why clustering outliers becomes a much harder problem. Okay. And the solution to all of this, and the solution that goes through all the different methods we've seen, that we will see today to do clustering, involves saying you don't want to choose between this approach and this approach. In other words, you don't want to wait till the end to decide for outliers or decide them all at the beginning. What you want to do is somehow run the algorithm for a little bit, use that information to give you a little bit of info about outliers, remove what you think are outliers, run the algorithm for a bit more, again get some more information, and keep doing this. And somehow that tends to work a lot better than either of these 2 approaches. So again, it seems natural, but the hard part is, okay, how exactly are you going to do this, and how are you actually going to say that you've done something reasonable? You just haven't made up some violent hack. And so that's what we're going to see. But before we do that, there is yet another technique that actually might be useful under certain circumstances. And I'm going to put just the one word down, and I'm going to let you ponder over what that might be. So the clue is sampling. How might you use sampling to help you? So first of all, the thing you should think about is, why would sampling be a good idea? Why should I even imagine using sampling as a way to deal with outliers? With any kind of randomized strategy, you have to think of that first. Why do you think this should work?
Is it uniform sampling?
Whatever you want. I don't say anything yet. You do whatever you like. Yeah?
Because you probably won't get the outlier.
Why not?
If it really is rare, then it's
Yeah.
unlikely.
Exactly. So the basic premise here is that, okay, we think sampling might work because we know the things that are bad are rare. So intuitively, if we try to sample from the data, we hope that our sample will not have those bad points. Right? I mean, think of it this way. I have a whole bunch of points here. Right? And I have some small fraction that are outliers. And I'm telling you it's a very small fraction. That's our basic premise. An outlier is not common, they're rare. This is a case that's, normally for sampling algorithm, this is a bad thing, right? You want the thing you're looking for to be plentiful. But here, in fact, you're looking for things that are not outliers, which are plentiful relative to outliers. So you do hope that a sample, if you just sort of hit from here, will not hit any of the outliers with some decent probability. And once you do that, you'll cluster your sample. But if you're going to cluster your sample, what do you hope for from the sample? I mean, we've talked about how to do random sampling for clustering before. What is the challenge there? If you now forget outliers, let's say my sample is great. I ignored all the outliers, and I just want a sample. What's the problem now? Can I be sure that I've got a good answer to my clustering problem just by sampling? What could go wrong here? And we've talked about this before, right? What the challenges are, especially in the big data realm. How do you, can sampling actually help you doing clustering?
You never know that the sample is going to reflect the population.
You don't know if the samples will reflect the population. Yeah, that's one point, and that's an important point. There was another comment somewhere from here.
We don't know what the distribution of.
Right, so that's the thing. Yeah. So you don't know, and in particular, you could have a bad situation if your clustering on the non-outlier data look like this, right? If you have something like this, then a sample will probably pick up points from the big clusters. It may not pick up points from the small clusters, because the small clusters have the same problem as the outliers. They're not that common. They will probably be bigger than the outliers, but they're not that common. Having said that, let's see how far we can push this idea, even under this problem of dealing with differential cluster size. Okay, let's see if we can make some assumptions that might go down. So let's say that we're going to do a uniform sample. So it's a uniform sample of the data. And let's say that we have, so we assume we have Z outliers. Okay, we don't know what Z is right now, but let's say it's some parameter. Let's say we can use it in our model. Okay. So now I'm going to sample a uniform sample from the set. And let's say I'm going to sample S items. So I'm going to sample S items from the set. And let's say the set is of size n. So there's n points here, you expect Z points here. Okay? Okay. What is the probability that I do not pick up even one outlier? Well, what's the probability I pick up no outlier with the first sample? If I do a uniform sample.
N minus G over N plus. What is the N total?
Z. Total size n.
N minus G over N.
Right. So it's basically the probability of the first sample not hitting the outliers is 1 minus Z over n. But I have to do this with every sample, right? I don't want to pick even one outlier, because that could just confuse me. So it's like this, right? And if the number of outliers is small enough, we can use a standard approximation. Say this is something like 1 minus Z times S over n. Okay? So this is the probability of no outliers in sample. Okay, great. But as we said, that's not enough. We not only want to not pick the outliers, we want to sort of pick the clusters. And let's say our way of sort of picking the clusters is to say we want to pick 1 point in every cluster. Okay? That's our only requirement. Now this is going to be very hard to do if we don't know what the clusters look like. Because if a cluster has 1 point in it, then the probability of picking that point is 1 over n. It's going to be horrible. So let's assume, so this is the key, assume that clusters are not too small. Okay? In particular, this might seem a bit strange right now, but it'll make sense in a bit. Assume that there are k clusters. Assume that each cluster has at least k times Z points in it. Okay? So if you think of it this way, you want clusters to look significantly better than the outlier set. So if the outlier set has Z points in it, you want each cluster to be much bigger than that. So it's k times. And again, this number is not set in stone. It's a result of some analysis, and we'll see what it is. So if I tell you now that each cluster has these many points in it, and I pick a sample, what is the probability that I pick 1 point, at least 1 point, from every cluster? So again, what is the probability of missing every point in the cluster? So if I look at any particular cluster and I sample points, what is the probability that that my first sample misses a point in the cluster? So the cluster has kz points. The probability of missing it is 1 minus kz over n, right? So the probability of missing all points, so the probability of missing 1 point in the cluster is 1 minus kz over n. The probability that no sample point hits the cluster, so it's a different problem, right? In the case of outliers, you want the sample to miss every point in the outlier set. Here you want the sample to hit at least one. So the bad event is missing all. So to miss all, we've already seen this, will be something like this. Right? Therefore, the probability of hitting at least 1 point in a cluster is going to be this. Okay, but this has to happen for every cluster. So now you have to do this. Right? Because now it's an and or thing going on here. And again, you can use various binomial tricks to simplify this as well. And this basically works out to something like 1 minus k times an exponential in minus k z s over n. Again, you do the usual, 1 plus x is e to the minus x tricks, and you can do this whole thing. So we want this probability to be high. We want this probability to be high at the same time. So we want to choose S to make sure both these numbers are big. Okay? So here's the question. So here's the idea. Set S equal to n over 2z. And if you think of z over n equal to alpha equal to the fraction of outliers, this is basically 1 over 2 alpha. Okay? So as the number of outliers gets smaller, you can actually pick more sample points because you're not going to hit them. If the outlier set gets big, then sample size is going to get small because now you run the risk of not hitting an outlier if you take too many sample points. Right, so Z is controlling how big your sample size is. It can't get too big because it'll start hitting them. But this is controlling how big it needs to be to actually hit all these points. So you plug this in. So if you put S equal to 1 over 2 alpha, then the probability of no outliers in sample is equal to half. That's why I put the 2 there. So that's a reasonable probability. Again, you can change the 2 and make this number bigger or smaller as you do. And then the probability of picking a point from each cluster is going to be much smaller. It'll be something like 1/4. So not very big. But again, and with random sampling, the idea is that you get a constant probability of this good thing happening. And so there are ways to amplify this constant probability to be a really good probability.
Where did you get these numbers from? 1 by 2, 1 by 4?
1 by 2 comes directly. You just plug in this number here
Okay.
to get half. This number takes a bit more work. You put that number in here, you do some exponential tricks, and you can say, okay, this is roughly going to be 1/4. It's not exactly 1/4. It's kind of, as k gets larger, this gets easier. So, and once you do that, you just run your regular algorithm on the sample. And the trick is, since you guaranteed by this process that every cluster has at least one representative in the sample, the result you get is not going to be the best clustering solution, but it'll be kind of close. For things like k-center, because of triangle inequality, you can show it'll be within a factor of 4 of the right answer. So again, this is not an important point, but the intuition is that if you have 1 point in each cluster, and you're doing k-center clustering, then the worst case, what happens is that you have a cluster, you want the center, you pick some point that was very far away from the center. So your estimates of the distances are off by a factor of 2. And they were off by a factor of 2 anyway, so you lose a factor of 4 overall. But it's not much worse than that. So you can get a reasonable answer from the sample. Okay, so your algorithm is basically, your new clustering with outliers algorithm is, number 1, sample S points. And number 2 is run clustering on sample. And then once you have the clustering, you can now put back your points, and points that seem to fall outside the clusters are the ones you throw away. So essentially you've been able to cluster data in a robust way by ignoring all the outliers. The only problem is this guarantee, right? You need 2 guarantees here. So you need this guarantee here, and you need this guarantee here. And that can be a problem. So for example, suppose you say that, I want z over n to be roughly 0.1%. So I expect that my data has 0.1% outliers in it. Right? So what's this going to say? That means you need to sample something like 500 points. Right? So S, by this formula, is going to be something like 500 points. And let's say you want 10 clusters. So you want 10 clusters. Right? So what you're saying is that each cluster must have at least 1% of the data. That's what the assumption was, right? K times E, 10 times 0.1 is 1, so 1% of the data. So if you have a data set where you want to find a 10 clustering, and you expect that the clusters are large enough that each cluster has 1% of the data, and you have outliers of the order 0.1%, then a sample of 500 points will get you what you want. Of course, if you change this now, let's say Z over N is equal to 1%, so your data is a bit noisier. So the number of outliers is 1%. It's still not a bad number. I mean, 1% outliers is not unreasonable to expect. But now if you do these calculations, what's going to happen? This is going to change. But now in your 10 clusters, each cluster must have 10% of the data. If you have 10 clusters and each cluster must have 10% of the data, what do you actually say? You're saying that every cluster has to be exactly the same size, and they have to exactly partition it. That's never going to happen. That's very rare. So while the sampling algorithm works if the number of outliers is really small, it starts breaking down with as soon as your number of outliers goes above a certain level. Because now the sampling rate you're going to expect, or the cluster structure you're going to expect, is just not going to be reasonable to expect. And if you make this number even bigger, like 2%, then it just breaks completely. Because now they're saying 10 clusters, each cluster is 20%, and that's not even possible. So sampling is an idea that works in a certain regime when you have, you do have very, very few outliers, but maybe more than 1 or 2. But it's a really tiny fraction. And you have some expectation about how many points each cluster has. Then this trick is very simple, because you can just run a sample and run whatever clustering you want to after that. But otherwise it's not going to work, and we're going to have to think more about it. Any questions with that? No? So again, there's a very back of the envelope calculation. It's not, I'm not saying you should take this very seriously, but it's helpful to see, to what extent you can use sampling. And in clustering, in general, you have these issues with sampling, that you have to worry about cluster distribution and so forth.
So here you're not making any distributional assumption, because in statistics there are lots of methods that try to find outlier, but they all make some assumptions about
Right, exactly. And the thing is, if you start off with a model that says, I assume my data is modeled by a collection of Gaussians, then your notion of outlier is kind of well defined. You can say, okay, anything that's beyond 4 standard deviations of the mean of a cluster center, it would be considered an outlier. And there are ways to do that. The challenge of outlier detection is when you don't have those kind of modeling assumptions to begin with, when you're basically doing a blank slate.
So these kind of algorithms, if applied on those where you do have underlying distribution, will they perform well on those tasks also?
That's a very good question. I don't know. We haven't, well,
I'm talking about parsimony, so why do we need those methods? Because there's like whole literature on those methods that they can perform without making any assumption.
because this is very weak, right? I mean, this breaks as soon as the outlier assumption size goes above a certain level. So this is not a solution to all your nodes. This only works under some very, very limited set of weak assumptions on data. If you know more about your data, you should be using more information. That's why you would want to use these more structured methods. But what I'm going to show you now are methods that, in the line of some of the algorithms I mentioned before, give you formal guarantees on the result you get without any assumptions. So you actually can do fairly well, much better than this, without making any distributional assumptions. But again, having distributional assumptions can always make your life better. So if you can incorporate them, that's great. It's when you don't have that clear problem.
So are there any clustering methods which are not affected by outliers?
Are there any clustering methods that are not affected by outliers?
Even if the outliers are there, and
Well, I don't know how they can be not affected. You can argue about which ones are more or less affected. Like K-center is definitely very unstable.
Yes.
The K-median is less unstable. But to say that it's not affected would imply that
They may
someone
be
the algorithm
affected.
knows to ignore those points. And then how does it do that?
they may be affected, but the clustering which I am getting is very good as compared to other methods.
Yeah, there is some folklore that say if your clustering result is unaffected by outliers, it's probably unaffected by anything. It doesn't matter what you do. This data is so clearly clustered that you can just eyeball it and get the answer. There's some meta theorems of that kind. That, the data is only hard to cluster when it's not useful to cluster it. So, but anyway, so there may be, but it's the thing is we don't know ahead of time. And that's again, outliers are one of those, you have some data, what do you do with it kind of problem. So what we're going to do is now, we're going to look at a way of actually generating a formal guarantee on how to do clustering outliers using this idea that I mentioned before, where kind of you on the fly, as you run your algorithm, start getting clues about where the outliers are. Okay? And so we're going to look at two different ways of, two different standard approaches for clustering that we've seen before, k-center and hierarchical clustering. K-median is similar to k-center, and I'll also mention k-means briefly. And we're going to take the k-center algorithm and kind of revisit it, look at it in a different light, because that will allow us to give us an outlier-friendly version. So you all hopefully remember the Gonzalez k-center approximation. Take the point, take its furthest neighbor, take its furthest neighbor, keep doing that till you get k-centers, and you're done. Right? It's very simple. Let me rewrite that algorithm in a different way. Okay? So instead of doing the furthest point trick, here's what I'm going to do. So step one, choose an uncovered point. So in the beginning, we'll assume all points are uncovered. Choose an uncovered point. Okay. Oh, sorry. Step 0 is guess the optimal radius. So the optimal cost of the k-center clustering. Just guess it first. Okay. Choose an uncovered point and cover all points within distance 2r of peak, and then repeat. So I claim this is a reformulation of the k-center algorithm with the same guarantees. So in this version of the algorithm, you take a point, just like you did before, use this guess for the optimal radius r to cover all points within radius 2r. Not r, 2r. Okay, they're all covered, so basically you've thrown them away. Repeat. So now you pick a new point, which is guaranteed to be distance 2r away from this point, because you've covered everything else. You don't know what it is, but it's going to be at least 2r away. So you can then cover that. So if you think about collection of points, right? In the case of the clustering, what you're basically saying is, oh, take a point here and cover everything around it. Take another point somewhere else, maybe here. Take a ball and cover everything around it. Take another point somewhere. Take a ball and cover everything around it.
So R is kind of like a threshold.
Sorry?
R is.
Yeah, R is your guess.
No, it's kind of like a threshold.
It's like a threshold. Rather than saying I go from here to that end, in other words, in the normal k-center algorithm, you kind of get to R at the end, because you keep picking points that are as far away as you can. That distance gets smaller and smaller. At the end, you reached R. Here, you're saying, let me just guess R up front instead of wasting time. I'll just do this. Because eventually, that's what's going to happen, right? Things within radius 2 are going to collapse. 2R is because of this 2 approximation. You can't actually guarantee that it's within R. And it's not hard to show that this will give you the same guarantees as before. In fact, it's a reworking of the same algorithm. It just runs it backwards in some ways. Of course, you have this issue of guessing the optimal radius R. And for now, we'll just say, okay, well, you have to guess the radius. Just here's a trick. Suppose I guessed a radius that was too small. Suppose I guess, oh, my optimal radius is 1, when actually it was 100. What is going to happen after I do this after k times? So I'm going to do this k times. I want a k-center clustering. I'm going to take a point. I'm going to cover distance 2. Take another point, cover distance 2. If my true answer was 100, and I did this with 2, what's going to happen after k steps? I'm going to have a lot of points left over, right? That I couldn't cover, which tells me, my guess was wrong. So you start with a low guess. If it's wrong, just double it, do it again. If it's wrong, double it, do it again. If it's right, you can back off. And you can essentially do a binary search. You can find the right value. Okay. So it's not efficient. And that's not really the point here. But it's a reframing of the original. Does this algorithm make sense? Do you all sort of more or less believe that it does what the original algorithm was doing, but in a different way?
Is there any way to determine R? So you run.
Well, that's what you said. You binary search it.
So you run the regular algorithm, figure out what.
So you guess R to be typically small, very, very small. And you'll run this, it'll fail, because you won't be able to cover all your points in k steps. You'll say, okay, I need to double R. So you double R. You do this doubling trick, it's the equivalent of a binary search, a one-sided binary search, and that you can get to R reasonably quickly. If you have, there are n choose 2 values of R, because every pair of points could be the value of R. So you do log of n choose 2 guesses. So log n times the time for one of these things will get you the actual answer. So you're doing a binary search. Again, it's not efficient. I wouldn't implement this in practice, but it's a way to get the same result. Okay? All right. But what this reformulation of the method is doing is telling you something actually interesting about outliers. I promised that when we came to an actual algorithm for doing clustering with outliers, it would implicitly be telling you what it thinks an outlier should be. And that's what's happening. Imagine that you ran this algorithm for k steps. At the end, you had a few points left over that you did not cover. And you were okay with it because these are the outliers. Based on this procedure, what property do those outliers have? So what can you say about points that are left over after k steps? Why are they left over?
They don't have any point vicinity of 2R from them.
Yes. They are far away from all the interesting points. Yeah. And let me modify this even further. Instead of choosing any uncovered point, choose the P with maximum uncovered points in ball of radius 2. Okay? So don't just choose any P, choose a P that gets you the most stuff to cover. Try to be green. And I want to make that modification because it now tells you a second thing about these outliers. Not only are they far from points, there are not many points in the neighborhood either. So this goes back to the density comment you were making earlier. Right? These points are both far from everything and they're far from each other. Because if there were lots of points that were far away, but there was a dense group there, eventually I would say, oh look, there's a point here with lots of uncovered points with the ball, I would pick them. They would not be an outlier. So the outliers that this algorithm is going to sense have two properties that we might agree are good properties for outliers. They are far from everyone and from each other. There's no such thing as an outlier cluster. Well, there might be, but that's not the kind of thing we're finding. We're finding these little straggly points that are spread out over the space. Okay? So a point that you don't cover in this process, if you end up with points not covered, has these two properties. And in some sense, this is the implicit definition of an outlier that we're going to be using. Okay, so this is the picture you should have in your head. Points are kind of... Again, which conforms to what you might think of as a natural definition of outlier, but I'm just making it more precise. And so now, here's the beautiful thing. If I want to compute a k-center with outliers, so in other words, you can think of saying, I fix the number of outliers z, and so there's a z star, well, there's a z, and and you say, what is the opt cost for this point set with k points, k centers and z outliers. Okay, so let's say I want to find the optimal k center cost with z outliers for some fixed value of z. And I want to run some algorithms. My algorithm will look like this. Choose point with maximum uncovered points in ball of radius 2r. Cover all these points. And you're like, wait a second, you just wrote that algorithm out. It's the same thing as before. So I lied actually, this is not the same algorithm. I'm just going to make one change. That's it. And the resulting clustering you get, okay, So after you pick k points, the resulting cost you get, you can show. So the cost of your algorithm is going to be less than or equal to 3 times the optimal cost for again, k points and c points. It's actually a very beautiful method. It's called the robust k-center algorithm. So the result that was proved 10 years ago, 10, 12 years ago. So just making one little change in a reformulation of a very, very standard algorithm for clustering allows you to get a new algorithm that has guarantees with respect to outliers for k-center. And it's based on this intuition that outliers are things that are far from everyone and far from each other. And so the work, the analysis is a bit tedious. I mean, not tedious, it's actually clever, but it takes a bit of work to prove this. You need it's what's called a charging argument. You need to prove some things. But that's all. And again, there's this sort of uncomfortable thing about guessing the value of R. But apart from that, any questions with this?
Will that upper limit change with the radius?
No, it's always 3. Yeah, the 3 is from the analysis. That in fact you can show, and this is kind of cool as well, just like you could show for k-center, that in an arbitrary metric space you could not, we don't think, you can't do better than 2. You can show here you can't do better than 3. So this is basically the best you can do. You actually cannot do any better than this because it's NPR. Well, unless we, it's NPR to do better than 3. So this is pretty much the best you can do, and it's very simple. It's kind of nice. And this again is for k-center, remember, right? We're doing a k-center approximation. If you want to do k-median, it can be done. The same group of authors who proved this show that you can do something similar for k-median, but it's a lot more complicated. You don't have this nice base algorithm to work with. You actually have to work with an LP, and the guarantees you get are also weaker. But you can sort of, so I'll put within quotes, you can sort of get a result for k-median, where basically you approximate the number of outliers and you approximate the cost. It's all a bit weaker than that, but there's some constant. So this is what you can do for k-center, and you can actually prove a nice bound here. For k-means, there's another heuristic which is actually very similar in flavor, without a guarantee. And I think this is an interesting, open question. Can you prove a guarantee for doing k-means? Maybe can you? Let me tell you the method first, and then you can see it might be interesting. So again, for k-means, the problem is the following: you run your, so let's say you're running your k-means procedure, right? The algorithm, take a bunch of points, or guess a bunch of cluster centers, assign every point to its nearest cluster center, take the average, and repeat. Right? The usual. But the problem there, of course, is that if you now say, I assign points to the nearest cluster center, there's some outlier. So it gets assigned to a cluster center and then pulls it back towards it because it's very far away. Right? So I have a bunch of points here. They got to get assigned to the cluster center. And now this point just happens to be very far away. This also gets assigned to that. So in the averaging step now, when you average, this new cluster center starts getting pulled out this way. And that's not a good thing. So somehow again you want to stop that from happening, and you want to do this during the algorithm itself. So let's write out the regular k-means objectives. The k-means algorithm, not the objective, says, assign points to cluster centers, right? And then recompute centers by averaging. You just repeat these steps over and over again until you converge. And we talked about how to initialize this to make this actually. So the new step you do here, which is very similar to what you might do there, is in the middle. And I wonder if anyone can tell me what you might want. Again, the same idea. You want to use the information you currently have to make some guesses about outliers. And let's say I'll even tell you that I expect there to be, again, z outliers. So I know that there are z outliers. What might I do to detect these points? What do you think? can you use the information you have so far about the clustering to make a guess as to who the outliers are? What do you think they would be? I currently have a set of clusters. I know there are Z outliers. What do you think those points are likely to be? And again, I only have to make a local decision. I'm not saying that I know the answer for all time. I'm saying at this moment in time, based on what I know right now, what might be the outlier points? Yeah.
See that are farthest from all the cluster centers.
Take the points that are furthest from all the cluster centers. Yeah, congratulations, you've just written a KDD paper. No, I'm serious, that's what it was. So the idea here is that, sorry?
If only it were so easy.
If only it's so easy. The idea here is that if there are outliers in the data, and I believe this clustering is a good one, then I believe those outliers are far away from the cluster centers. So the step here I do is find the Z points furthest from the cluster centers. So in other words, for each point, look at the distance to its closest cluster center, sort by that, and take the top L points, top Z points. Okay? Okay, what do I do with them now? So, hey John, you're a KD paper. So I have these points, now what do I do? I found them, now what?
I'm afraid reviewer 2 is.
You need a follow-up journal
rejecting
writing, so,
me.
sorry?
I'm afraid reviewer 2 is rejecting me.
Oh my god. So, no, but what do you, how do you do step 2 now? Given this knowledge, what might I do for step 2?
Remove them from average.
Sorry?
Remove them from average.
Remove them from the average, right? Because the whole point is the outliers. We don't want them to be used to influence the average, so you remove them. Very good. So you remove them. Removing outliers. Yes?
Nothing. I just said she might collaborate.
Oh, yes, yeah. Well, there were two authors in this paper, actually. Okay, wait. We got one more. We got room for one more author. What happens the next step? What do I do with these points?
Check that if they have some cluster defined by themselves.
But we don't expect that to happen, right?
The next step is.
What's the simplest thing you could do in the next step? Really the simplest thing you could do when you get back to the talk. The really simplest thing you could do. No, I'm serious. I'm not joking here. What is the simplest thing you could do in the next step? Do nothing. Forget that you found these points.
Yeah.
Why? Because these points I found based on my current view of what the clustering was. I don't want to bias the next round. So I find these points, remove them for the averaging, put them back in, so they can still be assigned to cluster centers. And then do this again. So at every step I get a new, fresh set of Z points. Okay? To pull out. At the end, I have one final set, and I hope that is the final set, because by this point I've learned a lot of what I know. That's it. This is the algorithm. It is called, fittingly, you are okay, K-means plus plus. This K-means minus minus.
You add those points again.
Yeah, because you only, so remember, we said that the problem with outliers was they messed up my center averaging. So just take them out for that purpose only. Be very conservative. Now, of course, with any k-means iteration of this kind, the first thing you have to show is that it converges. And it's not hard to show this converges. Basically, like all other k-means arguments, you show that there's a cost function, and the cost function reduces strictly. And so eventually this will converge. There are only a finite number of configurations, and you will never cycle back because you're always strictly reducing, so you will converge. You cannot prove anything else about this. So an obvious open question is, if we know how to make the k-means iteration provably good by applying the k-means plus initialization above it, what happens if you do that here? I don't know. So you have k-means plus plus combined with the k-means minus minus. I don't know what happens there. It gets very complicated there. But there's a nice question there about, can you actually give a provable guarantee like we have for k-center, but for k-means? So that's a question. But this is it's a nice heuristic. I mean, and the paper that sort of proposes this heuristic provides a number of experimental results that say, look, actually it ends up being fairly stable. If you corrupt it with some noise, it works. You do have to know z, which is one downside. But it's not the most terrible of downsides. Still. All right. So again, it's the same idea. You interleave your decisions about outliers with the running of the algorithm, because you believe that that algorithm is giving you clues as to where the outliers might be. You don't either do your decision up front or wait till the very end. You do it on the fly. The last thing I want to talk about today is the problem that comes up with, the usual problem with fixing k. So we have methods to compute, k-center or k-means with outliers, and you can do it for any value of k. But what happens if you change the value of k? So suppose I chose, I fix a value of k, and I have some point set. So as my point set, and I say, oh, okay, I ran this, k-center algorithm and with outliers, and I found these are the outliers. And now I change the value of k, and I do this again. There is no reason to believe I'll get the same set of outliers. In fact, I might get a different set of outliers. And I might change k again, and I might run it again, because I'm trying for different values of k, and I'm going to get a different set of outliers. Which is kind of strange, because you would think that outliers are outliers. They shouldn't matter on how many clusters you're using. Or you would like them not to. So what do you do then? How do you find outliers when it seems to depend on the value? And by the way, this is not a hypothetical situation. You can actually construct examples where, as you increase the value of k, things that were outliers become non-outliers, and things that were non-outliers become outliers, and this keeps bouncing back and forth. So you can get some pretty naughty examples, and in fact, you can construct an example on a line. So you just have a point on a line. You can construct an example where the set of outliers keeps changing as you increase k.
It's a very inefficient way of doing it.
Yes.
Not very elegant.
That's fine.
But you randomly come up with various values of k.
Yeah.
And every time you pick up whatever has been classified as outlier.
Yep.
And through that, from that list that you've accumulated across those loops, you find out the most common.
The most common one, single short variable. This is a very good idea. So yeah, if you don't know where the outliers are, you just run it for different values of k and do some kind of voting. Okay, these points keep showing up as outliers. They probably are outliers, and that's a good strategy. So so define outliers by voting. This is not yet a paper, but maybe you should be.
Actually, we have.
You have a paper. Okay, all right. So you already have a paper. So so you can do this. And I think that actually could work. It might be hard to say exactly what you're finding, but you definitely would find something. The things you did find, you probably have some confidence there really are outliers. But let me try to argue for another approach, actually based on a result that just came out this year, actually, which is kind of cool. That says that even if you could potentially have different outliers for different values of k, there is a way to construct a universal set of outliers that are outliers for every value of k. So instead of saying fix k first and then find outliers, you can say I'll fix the outliers first, and this works for all values of k. And in particular, we're going to look at how to do hierarchical ones, which is of course the way we think about dealing with multiple values of k. Okay? And what I mean is the following. That the goal here is to produce what I'll call a universal set of outliers. Okay? We'll call this set Z. Such that for any k, right, the cost of clustering P minus Z with k clusters, right, is close. So up to some constant factor times the optimal cost of a k-centered clustering with Z outliers, the data set. And the catch here is that this Z will have size small z squared. Okay, so let me sort of see what I'm saying. What you would, so let's say you're looking for solutions which have Z outliers in them, just as before. And there's some optimal solution for doing it. And I'm saying, okay, I want to find the set of Z outliers. For any fixed k, I can find a set of outliers and I can look at the solution. I want some result like this, and that's fine. But what I want is to reverse the quantification. I'm not saying fix the k first and then find Z. I want to fix Z first and then find k, and then do it for all k. And while I can't get a set that's exactly size Z, I can get a set that's close to it. Z squared. And there are reasons why you can't do any better than this. But so in other words, I am able to construct a universal set of outliers that works for any k, and in particular works for hierarchical clustering. So my new algorithm would be find the set first, remove it from the data, and then run your regular hierarchical clustering, and this is guaranteed to be close. We've already seen how you can get good approximations for hierarchical clustering, and we can use those methods here, and this result gives you the nothing else. So it's kind of very surprising that this is true, that you should expect to even see this, that there's this kind of common set that works for all values of k. In some sense, this is finding the thing that you're finding by avoiding. I think it'd be interesting to see whether there's a way to sort of, this algorithm is a little bit tricky. It'd be interesting to see if you could do it with something similar. But that's exactly what it's finding, the consensus set of things that work for all cases. And again, I'm not going to go into the proof of how this works, but I'll give you the algorithm, because again, the algorithm reveals some sense of what this is thinking of as not. Okay. So let me give you an idealized algorithm that assumes things that we don't really have in existence, and I'll show you how to replace them with things we do have. Okay. So okay. So let's see. So we assume that. So we'll assume for now, and I'll tell you how to remove this assumption. Assume we have sets O1, O2 up to OK, where OI is equal to the optimal set of outliers for I clustering. So in other words, suppose I fix the value number of clusters, let's call it I, and I say, okay, what is the set of outliers I need for this value of I? Let's assume we have all those sets. You know, there's no reason why I do, but let's just pretend we do for now. You know, of course, looking ahead, we will use one of those algorithms we just talked about earlier to find an approximation of that set. But for now, let's pretend we have it. Okay. So what we're going to do is we're going to kind of build up this universal set slowly by looking at these outliers and combine them in clever ways. Okay. So we start off with the first, so we start off with S0. We'll say S0 is going to be the set, you know, ST is at the end is going to be the set we're looking for. Start with S0 and we'll set it to be equal to the first one here. So the outliers for a one clustering. Okay. And then what we do is we go through this iteration. Basically from 2 to n. So for k equals to 2 to n. Okay. So we just go through all values of k because we're going to look at all possible clusterings. And here's what we're going to do. Suppose, so at some point we have the best. So we're going to have an index parameter t also, which I'll explain in a second. And this t is going to index the outlier set that we have. And the idea is this. Suppose the outlier set that we have is not quite good enough. Then we want to do some more work to add to it. And when an outlier set be not good enough, it would not be good enough if the current best value for K clusters, right? And Z outliers, okay, is much, much less than the best solution I can get by subtracting my current set, ST, and looking for K clusters. So let me explain this quickly. So what we're saying is that we expect to produce a set of outliers that are good for all values of K. That's our goal here. Okay? So we're going to build this up incrementally. And what we're saying is, suppose at some stage we have found, by magic, again, there's lots of magic going on here, right? Suppose we have found by magic that the best answer we get by subtracting the current set of outliers and running the clustering algorithm on the rest is not really good compared to what we really want. That's violated our claim that this outlier set was good. So now we need to do some stuff. Okay? And that's when we'll increment. And then we'll do a bunch of stuff, and then we'll repeat. So the whole process is, take your current set of outliers, the guess that you have, see if it's good enough. If it's good for this value of K, move on to the next value of K. If not, do something. Okay? So what's something we have to do? So the something we have to do now is to say, oh, look, the current set of outliers is not quite capturing things because maybe there's some outliers we missed or something we've done. So we're going to modify some things. So we're going to create a new set, U. Let's call it UT. Now T has been incremented. So now we want to find ST plus 1, right? So the current set of outliers we have is ST minus 1 because T has been incremented. So let's say that this is the current set of outliers we have. And now add in the new set we got for K. The new set of outliers we had for that fixed value of K. Okay, so we have some outliers we built in from before. We're throwing in the new stuff that came from a fixed value of K. And we want to do something. This is our pool. This is our pool of outliers that we're going to pick the new set of outliers from. Okay? And we're going to look at two conditions. We're going to look at all points. We're going to find all UI belonging to this UT that satisfy two conditions, just like before. First of all, their large neighborhoods are in U. And I'll explain what this means. And their neighborhoods are not big. Okay. So let me explain what these things mean. We are looking at a sort of a pool of possible outliers. We've said that outliers are things that are in sparse regions, so the neighborhoods are not big. And I'll make this more precise in a second. So that's one property we want these points to have. We also don't want them to be too close to good points. So if their neighborhoods are still in the current set of outliers, right, then they are not close to any good points. Again, they are far from everyone else, and they're far from each other. That's what these two conditions are saying. They're far from the good points here, and they're far from each other. And to define neighborhood, I'm going to use the current opt cost. I'm going to say, okay, this is like, if you think of k-center clustering, the optimal cost of a k-center clustering is the radius of a ball around a point. So let's look at this radius. And so when I say big, I'm going to say, when I'm going to say neighborhood, it's going to be a ball. So I have a U and I have a ball around it of radius twice the optimal cost. Again, that twice always shows up in these things. So we're saying if this is the optimal cost for k clusterings, let's look at a ball of radius 2 opt, just like we were doing there. That ball should not have many points in it. It should be sparse. So big is going to be less than or equal to z. Z is the number of outliers we want, right? And their neighborhood does not contain any good points. It only contains bad points. Things that you've declared as outliers so far, and things that are outliers for this value of k. So they're far away from good points. In particular, they're at least this much distance away from any good point, which is again the criteria. So this algorithm looks a bit tricky, but it's really not. It's using the same idea that we've seen over and over again. Outliers are things that are far from good points and far from each other. So you have these two properties here. So once you find all these points, you pick them. So these points are the intersection of these two properties. And now your new S, ST, is equal to the set of all such UI. And you keep doing this over and over. At the end of when this whole process is over, the set of points you have is your universal set. And there's a proof that says the set is size at most equal. So once again, the same idea shows up in K-center, to some extent in K-median, shows up in K-means, and now showing up in hierarchical clustering, that outliers are things that are far from each other and far from everyone else. And what's cool and very, very surprising, at least to me, is that doing this trick, you can get this universal set that works for all K. It's a very clever idea. And I should say that the constants here are not particularly great. When a group of authors doesn't actually say what the constant is, you know it's not a good one. There was a 28 floating around somewhere, and that kind of got absorbed into a even bigger constant. So that number, the final constant is very large. Nevertheless, the fact that it exists is interesting. I would not have expected something like this. And of course, this is not a real algorithm because I have all these imaginary magic components to it. How do you find this? How do you find this? How do you find this? Use the algorithm we had before. So we had this K-center algorithm that gives you a 3 approximation and gives you outliers. Use that to construct these sets. So you'll get these sort of modified sets, but there'll be sets from the algorithm. You need to compute this quantity, you can use it using the algorithm. Again, it's kind of modified. You need to compute this, well, just compute the cost. Find the best K-center clustering using any other algorithm you want, like Gonzalez, and then compute this cost. And it turns out if you replace all of these by their approximations from using known subroutines, everything still works. The proof still works, everything still works. We just change the constancy. So this gives you an actual algorithm to find this universal set of outliers to remove. And again, you're adapting on the fly. You're sort of using the structure of the clustering you found so far to decide which points to add into the next round, rather than deciding anything. Okay. All right. Any questions? So this is all, I'm not going to say anything more about outliers in the class. This is about it for one lecture. I think, I always thought of clustering outliers as a very messy problem, but I think these couple of papers, some of them are old, but some of them are newer. Like the K-means paper and this paper are within the last 2 years. The other paper for K-center is much older. I think they have shed some new light on what is it that makes outliers in a way that we can find them usefully. And these algorithms are helpful to understand that. You could argue that this is not a reasonable definition of outlier, that maybe there's a better way of defining it, and that would be fine. And then you'd have to look for what algorithms would be suitable for your definition of outlier. But as I've always said with clustering, the issue is not what's right or wrong, the issue is making your assumptions clear and open. And that's what we're saying here. This is what we define outlier, and then we can do this. All right. Any questions? Okay, very good. See you on Thursday.